Leah here from LeahForSci.com, and in this video I'm going to solve question 1 of the Organic Chemistry 2 final practice exam. You can download the exam and solutions on my website LeahForSci.com/Orgo2Final. In question 1, we're told to determine the products of this reaction, and at first it looks scary, but the key is to figure out what we're looking at. Anytime you see heat and no reagent or solvent, and realize that you're reacting pi bonds, think of the Diels Alder reaction. The first molecule has a diene, so that'll be half of our Diels Alder, and this one, having an electron withdrawing group on it, has to be the dienophile. We know the reaction, but it's kind of tricky to figure out the next step given the rings and all the substituents, unless you put it into the standard form trick that I teach in the Diels Alder series, and that's to set the molecules up as follows. The diene gets the pattern 1, 2, 3, 4, and the dienophile gets A and B. We know the product of this reaction is a cyclohexene, where we have 1, 2, 3, and 4 fused to A and B, with a pi bond between 2 and 3. Any other substituents on the molecules will just follow the numbers. So let's start with the diene. We know that this is the portion that will act as the diene, so we'll number it 1, 2, 3, 4, and then set it up over here. 1, 2, 3, 4. Now we have to complete the ring with 5 and 6, but I don't want them to be in the way. I want to draw them out of the way, as you do with any bridgehead carbons. Just exaggerate the bond from 4 to 5 to 6 and back to 1, which is fine as long as 4 is attached to 5, which is attached to 6, and back to 1. Let's not forget the OCH3 on carbon number 2. The dienophile is pretty straightforward. We have a pi bond. That'll be A and B. The question is, do we label it A and B from the carbonyl down, or do we label it A and B towards the carbonyl? For this, you have to look at what groups we have and how that impacts the electronegativity and the resonance of the molecule. The diene has an electron donating oxygen on carbon number 2. If these electrons were to resonate onto the pi bond, then these electrons of the pi bond would resonate towards carbon 1, making carbon 1 partially negative. Now let's see how the dienophile can resonate so we know where we have a more negative or more positive carbon. The electrons on the pi bond will resonate towards the carbonyl carbon, causing those electrons, the pi bond between carbon and oxygen, to collapse onto oxygen. This makes the lower carbon, meaning the one furthest away from the carbonyl, partially positive, and the oxygen partially negative. If we have a partially negative carbon on the diene, we want to line up the more partially positive carbon of the dienophile next to that, and so we draw it as follows. We have the pi bond. This would be our partially positive, and that means the carbonyl is all the way down here. Now that we have it set up, we proceed with the reaction. We have a concerted mechanism where all the electrons move at the same time, giving us a cycloaddition. Drawing the product looks scary, so don't even look at your starting molecules when you're first drawing the product. Instead, we'll just draw a cyclohexane, because that is the product of a Diels Alder reaction. 1, 2, 3, 4, A and B. Now let's look back at what we have, and let's not forget the A and B over here. Starting on the diene, I have an OCH3 attached to carbon 2, and since carbon 2 is pi bound to carbon 3, it's sp2 hybridized, it is flat trigonal planar, so the OCH3, the methoxy group, doesn't come out of the page or go into the page, instead it's in the plane of the page. What we also have are 5 and 6 coming up as a bridge, as another fused ring, so I can draw it as I see it, or I can just pop them in here as 5 and 6 and just show it like that, as a bridge coming up out of the page. Then we'll move on to the dienophile. A and B are on the reactive carbons, but let's not forget the ring formed with C, D, E, and F, where F has a carbonyl. So we just add that in. C, D, E, and F. F binds back to A, and F has a carbonyl. One more thing to keep in mind here is that when these add, they add to the top or bottom face of this molecule, meaning it'll have the substituents on A and B pointing up or down. But because we have a bridge here, we want them to be opposite each other so there's no steric hindrance and no interference with the molecules. You can see these molecules written in a lot of different ways. One of the most common ones is the breadbasket, so let me show you the product in that form. We have the cyclohexene product drawn not quite like a chair conformation, but drawn where you actually see the side angles of the bonds. Don't forget, we still have 1, 2, 3, 4, A and B, with a pi bond between 2 and 3, an OCH3 flat or trigonal planar with the carbon at 2. So we're not showing it up or down, we're showing it straight. Carbons 5 and 6 are shown kind of like a handle to the breadbasket. That's why it's called the breadbasket form, coming up as a bridge out of this page. And then we'll show the ring attached to A and B. We want to show them down, so it's the opposite orientation. That's C, D, E, and we already have F. And let's not forget the carbonyl on carbon F. Be sure to join me in the next video where we solve question 2. You can find this entire Orgo 2 final exam with the solutions on my website, layfirsci.com/Orgo2final.